Welcome to our second Krones.digital Tech Talk. Today we are going to host it from the beautiful Prague. And we have recently opened office here. And my name is Emil Dietl. I work at Krones for at least 5 years right now. I'm a technical lead for cloud software. And I have brought Florian with me. Hello, Florian. Maybe you introduce yourself.
Yeah, thank you, Emil, for introducing me. My name is Florian. I'm a senior solutions architect with AWS. I'm a specialist for streaming applications, such as Apache Kafka or Apache Flink, also Amazon Kinesis, and all the related ecosystem. And today we want to talk about how Krones is using Apache Flink for monitoring their production lines. So please, Emil, go ahead.
Yes, sure. So what we are going to perform is a tech talk. So we want to give you some insights of our technical journey as Krones Digital. As you might heard, Krones is a leading manufacturer in the liquid food industry. So Krones delivers everything what is kind of liquid and needs to be filled into bottles. And so what can you expect from today? So we bring technology insights, we share best practices on our journey. So we had an opportunity to learn a lot while implementing, let's say, production crucial software. And so one of those kinds is real-time data monitoring. You have probably seen it in the title. So what we wanted to do as Krones is, so you have to imagine we are producing a lot of bottles in let's say in a short time range, and so there is a potential of a lot of failures. So we need to somehow monitor those and improve the production yield. So the problem is whenever there is a problem and the production gets stalled, the overall yield decreases, and we need to get, let's say, in front of that and detect everything earlier before it actually happens to be able to enable streamlined production. Further, we actually kind of need to monitor operators there in the production line. You have to imagine Krones delivers the whole production line for producing bottles, and there's a lot of, like, let's say, operators required to work on that, and so they need a proper notification when something goes wrong. And so we came up with the idea of building a real-time data monitoring system to actually be able to cover all those use cases. Further, we want to calculate metrics from machines and to be able to cover like averages to monitor those as well. So nothing, let's say, is as stable, and so you need to have some statistical measures to perform that. And so we can do that actually with support of machine sensors. And actually, we want to create rules and create those so-called monitoring scenarios. The business idea behind that is that as well as Krones, as well as users, in terms of users, we see people, they can, customers, they can actually buy this kind of digitalization software for Krones lines. And so they need to create the rules by themselves, so they should be able, as well as, but Krones also want to have insights in the production and also derive logic out of it, and to be able to deploy it on customer side to bring them benefits without them having to intervene with the data itself. So that makes it a lot of easier for the customers, and also Krones can proactively monitor the state of their production lines. So where we are right now, let's say there's always a history behind every system, and eventually everything gets let's say, technical depth at one day, to be specific to that. So we started out pretty naive. So we saw, well, machines, they're producing data. Why not collect everything in a time series database and then perform queries onto it and try to get something out of it? And let's say that we call rule evaluation. So the basic idea was pretty easy, and we started out to do that. But at some point, we found out, well, queries are really hard to debug, and if you want to find problems, it's really hard to find them. So it didn't work out the way we expected it, and the major thing I saw in a different presentation about Flink, but it was actually pretty smart to say, well, we're not interested in state at all, so we don't want to query all the data set what we have collected, so we are interested in the state transition, and that nails the point directly. So we want to get notified when something changes and not query some state to detect, well, there was a change, but well, now it's gone. And even though the data is hard to query, and so, well, we came up with a slightly different idea. And if you talk about rules, so, well, there are a lot of rule reasoning systems, but we found out we have to define our own understanding of rules and how to deploy that in an environment. And so our rules are built up in terms of, let's say, groups, and those groups, they need to exist because imagine you want to monitor something and there's, let's say, a maintenance task. A machine produces a lot of data during that, but is not related to production. So you actually don't want to, let's say, those rule detects deviations in the process while a machine is not in the correct state or is not running the right product. So there has to be, let's say, some filtering before that. And so we said, well, there might be some idea of a grouping. So we put everything in a group. And then there's another group that says, well, if the machine is running or some other state I want to configure, there's also temperature sensors, pressure sensors, and all kinds of stuff that has to be like sending data for at least 5 minutes, and there's a lot of different concerns. And so, and also we want to combine them logically. That means if a temperature is above threshold or something else, or we want to combine it with it, and to give a user more flexibility, because sometimes data is not that easy to interpret, and you need to have some handling to overcome some, let's say, data hiccups and stuff like that. And so all of that in terms of reasoning results in a state. So we return a state for each of these groups, and then, well, let's call it agenda, and this all sums up in some sort of agenda, and then it gets processed with proper weights that we apply to the state, so that we can say, well, if a machine is not running, we don't want to do further reasoning, but if the machine is actually doing that stuff what we expect, we want to monitor it accordingly. And that led us to the, let's say, overall thing. And you can see it from this, let's say, left to right stream. So somehow this is related to streaming. And then, Florian, let's explain a little bit about streaming and how this adds up with Flink, if you want.
Yeah, sure. Thanks for the introduction, Emil, on the product itself. So let's discuss on how we do data streaming. So basically, a data streaming application consists of several layers. So at the very first, we have a source. In the case of Krones, this might be a production line system, something that produces data. This can be pretty much any system that we have. This can be some containers that we run in the cloud or physical machines, whatever you can imagine. At the next step, we have some ingestion layer. So an ingestion layer basically allows us to ingest the data from our source into our data storage. Our data storage, also called stream storage, is where we will buffer our records. So very common, Apache Kafka, Amazon Kinesis. There are also some new Apache projects coming up. Apache Pulsar, for example, might be something you have heard of. Those are all stream storages. And the very interesting thing is stream processing. And this is exactly what we will be looking at today. So there exist a lot of stream processing frameworks, Apache Spark, Apache Flink, Apache Beam, a lot of others as well. But we will focus today only on Apache Flink, because this is also what Krones is using. There's also destinations. So this is the last step in our streaming layer, I would say. Those are usually databases or data lakes, data warehouses, pretty much anywhere where you want to persist data for a long time. So let's have a look at Apache Flink. What is it actually? It allows us to do stateful computations on data streams. Those can be bounded or unbounded. This basically means we can do it on data sets. For example, if you do some data engineering with Apache Spark, this would be most of the time a bounded data set, CSV files, Spark-key files, whatever you're using. And unbounded data sets are data streams. For example, Kafka topics, Amazon Kinesis streams, or any other source that is not bound to a certain end. And Flink is a distributing streaming engine that allows us to process those, but in a stateful way. So if you have not heard about Apache Flink, this might be the time that you look at it. It's the most active Apache mailing list that exists out there. It has about 50 million Docker pulls in the last 6 years. And it's already proven at scale. So it's nothing that came up in the last few months or something. We already have a lot of companies using it at large scale. For example, Netflix, Uber, AliCloud. A lot of big companies are using already Flink in production. There's also a big conference. It's called Flink Forward. It's happening usually in the US. A lot of new features are presented there. So if you're interested in Flink and what's coming up, feel free to attend it. There's also an online version that is accessible for everyone. We have more than 1,000 committers. We also have a few from AWS. So AWS is also a committer of the Apache Flink project. For example, we recently committed the async source to the Apache Flink project. We also do some connectors, Amazon Kinesis, or other AWS products. And we have really large organizations using it. So we see companies processing trillions of messages a day with Apache Flink. So it's really proven at scale. So why would you use Apache Flink? It's basically, you can build a lot of different use cases. You can do streaming analytics, such as Krones is doing. You can do ETL transformation for streaming data, if you, for example, want to ingest it in your data warehouse. You can also do batch analysis. So if you want to migrate some existing batch analysis workloads, or even create new ones, you can do this also with Flink. And this allows you to use a unified API for streaming and for batch processing. Flink is also very strong on processing guarantees. So you can decide if you want to use exactly once guarantees or at least once processing semantics. It has also a very strong late data handling. We will also dive deep very deep today on how Krones is doing that, how is it handling late data that arrives later to the stream than it should. And Flink is horizontally scalable. So we can scale our workloads to a very large scale, processing trillions of messages a day and up to terabytes of state. And there's a very strong community around Flink. So we have a lot of connectors for open source or cloud native products that exist. There's also Flink Forward. So there's a lot of community events going on around Flink. And in the next few slides, I want to discuss some Flink concept and application architecture patterns that are used. So if you deploy a Flink application, this is what you will see most of the time. So if you deploy it on Kubernetes or on your own laptop or, I don't know, virtual machine, you have basically three components. A job manager, which is basically responsible for the jobs, pretty much what it says. And you have workers. Those are called task managers. And task managers are actually doing the job that we define in our Flink job. So let's say we want to define a source that is reading from a Kafka topic and then sending it downstream to a database, for example. This would be an execution that is happening on a task manager. And a task manager offers several slots. A slot is basically a certain amount of CPU and memory that we can assign to execute our subtask. And very important, you see on the very right, is our durable storage. This is used for snapshots. So if we want to recover our application, update our application, we need some state that we recover for our application. And this is usually stored outside of the Flink application. So if we talk about stateful processing, this is a very, can be interpreted in a lot of ways. So what is actually stateful processing? This means if we receive a lot of events from our data stream, and we want to analyze them not one by one, but to have them analyzed in a group. So this means that past events can influence the actual results of the data stream. So let's see here on the image that we see, we have event generation. So this basically is some event we receive from machines or, I don't know, from containers, metrics, whatever. And we send it to our Flink job. We only see here our task manager, but this task manager is running our rich operator. So rich operator basically means that it has access to state. So it's possible to store something. This can be a single value, an array, a hash map, whatever you define. And rich operator sounds very complicated, but those are already built in Apache Flink. So if you want to do a simple sum function on a 5-minute window, for example, this is already built in. You don't need to bring your own Java code. This is something you can do out of the box. And this rich operator is updating the state and also receiving the state from where it's stored. So by default, this is a RocksDB or a hash map backend that we can use. And after we process the state, we can emit results. For example, in our 5-minute window, we define we want to see the average of all the records, and then we can emit those results either to another data stream, to a data sink, whatever we want to process them. So how does AWS fit in here? So Krones is operating Apache Flink on top of AWS, and we have several ways to deploy Apache Flink. So on the very left side, we see Amazon EC2. So this basically means we can spin up virtual machines on our own, start our Flink cluster, our job manager, our task managers, and do everything on our own. So the infrastructure is provided by AWS, but you do everything yourself: scaling, recovery, operations. And to be honest, operating Flink at scale is not very trivial. So there are certain ways that you can reduce your operational overhead. For example, you can run it on Amazon EKS. Amazon EKS allows you to run a fully managed Kubernetes environment. So you can run it on top of Kubernetes. You can use a deployment yourself, or you use an operator. There's an open source operator. There's an AWS-provided operator. So this allows you to have automatic scaling, recovery, and built-in monitoring. So this is already much more managed than you would see on Amazon EC2. And there's a fully managed version as well. So if you want to decide you want to go fully managed by AWS, you want to look at managed Flink on AWS. So this allows you to just deploy your Java application on managed Flink without worrying about scaling, operations, logging, and much more. And next, Emil will present on why Krones choose to run their applications on managed Flink.
Yes, sure. So the thing is, when you want to get started with some business idea, you want to get started fast. And the thing is, what Florian anticipated is we actually had zero knowledge in running it at scale, and therefore a managed service comes into play. And it brings so much benefits in terms of we don't have any operational overhead, so we can get started right away, rewrite our code, deploy it. We can build up a CI pipeline. It's pretty much everything is like there. And further, we took all this like building blocks of streaming applications, like used Kinesis, Amazon Kinesis for streaming, that enabled us to easily build replayable streams. So I will dive into that a little bit further later on, how we are going to do that. And also that we don't need to think about scaling in any direction. So that made us so like the perfect fit for it. Sure, that there's arguments for everything, but that was the perfect fit. So we wanted to get started quickly. So, but basically now we have deployed everything, but there's no rule in there. So anything. So how did you get things in there? So there's a pattern, and Florian will describe that for us. Yeah, well, or I can do it. So the broadcast state pattern. So the necessary part is when you deploy a Flink job, it is pretty much static. That means it gets compiled into a cyclic graph, and that gets executed on the task managers that is driven by the job manager, what we have seen previously. And so you can change that topology at runtime. So once it is deployed, it's as static as it is, and that's a basic, let's say, also the feature of Flink. So what Flink offers to get things dynamically in it is the so-called broadcast state pattern. And as we saw that, a rich function that runs on an operator and an operator runs on the certain subtask, it can have a broadcast state. And the broadcast state is something where you can get definitions in and out. So that makes it really cool for us. Also, only get the time series data in it. So what we mean with the event stream, that's the data from the machines. And further, there's the control stream. So the control stream actually controls the processing. And so what we are able to do is we get rules inside the system. in action, it looks like that. Pretty much this is a high-level architecture. So we have a production side on the left, and users can create rules, and they get from different systems that they get put it into the rule definition stream and metric definition. So we also calculate metrics, so what I mentioned earlier. And further, you have the third stream that is processing the machine data. And so everything then gets into Apache Flink, and so we can basically use it. So there is an interaction then possible with the user and the Flink application without needing to restart the Flink application. So you can do that as well, but it, let's say, introduces some sort of downtime, and it is not like optimized for a user experience, because users always want everything right now, so you can't wait for 10 minutes to restart the whole cluster. And so how does that work pretty much? So I brought some minor code examples. So you basically, what you are going to do is you have a broadcast stream, and you need to connect it to your process function. The process function is a further concrete implementation of the rich function, so you can process elements there. And elements is meant by the event stream, so machine data, sensor data, temperatures, and all that stuff. And so the rule evaluator stands here for the so-called process function. And within those process functions, it's pretty much straightforward. So it's nothing complicated, because Flink brings a lot of like this managed complexity about scaling and all this stuff to us. And so we only need to process one element after another. And we can access within every element, we can access the broadcast state, and then we can create, so this is a simplified example, but we can get a certain rule out of it. It's basically a Java object, so you can work on it, and then you can, let's say, process your data points. This is the one thing, but we talked about scaling. Well, there is a scaling out of the box, but you have to decide when you do streaming in which direction you want to stream. So, and further, if you say, well, it's a distributed system, so things get distributed among physical machines, and you want to ensure that data for one rule is being routed always to the same machine, because imagine if you have two machines and the data is arbitrarily ordered. So, well, you cannot do any reasoning about the data, because you will process it on different machines. So that's why Flink brings in a concept of keying. So you can actually assign a key to a certain element, and then you ensure that always the same keys run to the same operator. And that makes the system pretty strong, because you can scale with the amount of rules. That is more or less our scaling, what we have chosen. Well, you can choose any other option, but this makes it for us pretty straightforward. And so we can manage a lot of rules in parallel. And so there is a real strong pattern of Flink, but you have to get used to it and how it works. So you might introduce some smart keying for the rules. And in this way, what we are doing is to imagine a rule, two rules are using the same sensor data. You duplicate just the data in order to process it on the different machines. So I talked about a little bit of running data on the same machine, and there comes a really necessary point to it. If you want to reason about event patterns, ordering is crucial for those kinds of events. And Florian, let's introduce some basic semantics of that.
Yeah, sure. So if you look up ordering or events in general in Apache Flink, you will read about event time and processing time. So I brought you a small example on what is actually the difference between event time and processing time. So if you see on the bottom, you see when each Star Wars movie was released. So if you watch it this way, you will have the processing time of each movie. So you can start with episode 4 and end up with episode 3. So this is the order as it was launched. But if you want to have event time, you want to watch those movies in order. So you want to actually start with episode 1, episode 2, episode 3. So it's not the same order as the processing time. And this happens also in streaming systems. It might be that some records arrive later because of network delays or just for some other reasons that can happen in systems, right? So we need to figure out how do we process those records if they're arriving late or at the wrong time. And there's a very distinction between event time and processing time in Apache Flink. So let's see this example. we see an incoming stream of records. Those are just random numbers. And those red boxes are basically windows. So we can define windows in Apache Flink. We say this is a 10-second window, and each record that we receive is in this window. So this would mean that we're using processing time, right? Because we use the time window that Flink is seeing. So we see it's now, let's say, 5 minutes after 6, and in 10 seconds, we just close the window, and everything that has arrived, and everything else we don't care. So this is basically how processing time works. So how would event time actually work? If we have the same records again, and the same windowing, we would probably see a record arriving a second late, but it still says, the timestamp says, hey, it's actually 8 seconds and not 11. So how do we do that in Apache Flink? So we can define a selector on our record. We say, hey, this is our timestamp. Just read the timestamp and use this as our event time and not use processing time. So this allows us to actually progress on event time. So if a record is arriving late, we can identify it. We see it's out of the window, but maybe we already implemented on how to handle it. So how do we implement how we handle late records? And this is called watermark strategy. So basically, this allows us to close windows. If you have a 10-second window, how long should we actually wait until we close the window and we say, OK, now our processing is complete? We want to see, for example, the average of the last 10 seconds. When do we know that this is actually done and no records will arrive? And this is how we define a watermark strategy. Flink has some built-in watermark strategies, such as 5 seconds late arrival is allowed. So this would, of course, mean that we introduce some additional latency, because we need to wait 5 seconds more because we cannot close the window yet. So there are already some predefined watermarks that you can use. But Krones obviously had some more specific requirements, and they implemented their own watermark strategy. So Emil, you want to introduce us how you solved this challenge?
Yeah, sure. So that was a kind of experience for us to see that, well, if you talk about the whole watermarking thing, you anticipate, well, it's pretty much straightforward. But you always, sometimes you forget about the data which is flowing in, and you can see it in those kind of architecture. So we have many production lines, and they're, let's say, scattered around Europe or some places, and they are all sending data into the system. So basically, what first comes into mind when you deal with distributed system, where there is network, and it would be actually pretty naive to say, well, it's always working like I would expect it. No, there will be delays, and there will be a lot of like connection losses and all kinds of stuff that can happen that will eventually happen. So basically, we use further to get deeper into the problem. Well, let's say, don't say problematic, but the challenge is actually how to get the data in. So the ingest is based on a component that is delivered by AWS, because you want to upload data from the edge into the cloud. So that needs to work in a way that network outages and buffering and bandwidth usage is as optimal as possible. So that's called what AWS delivers that into the Greengrass framework, and it's called Stream Manager. But what comes with it is some basic let's say, kinesis sharding strategy. And if you go deeper, maybe you're familiar with Kafka or kinesis. They're based on partitions or sharding, and you need to actually define it. And the stream manager defines a random number. What brings the benefit of an even distribution among shards, and a short, let's say, explain on that is the shard in kinesis gives the ultimate concurrency or parallelism that you can run, because you can run different machines on different shards, and they can read data from the kinesis stream. But what happens if your data is not together in one shard is that what the stream manager is doing, it distributes it evenly, so the work is evenly distributed. So imagine a counter in a supermarket. So if there are two, and there's a person in front of that, and saying to each of the persons, well, you go left and you go right. So there will be even queues, anticipated that the counters are both from the same speed. But anyway, that brought a lot of challenges for us because you call that once a stream, the elements don't arrive in order, you say, well, this is some kind of out of orderness. And so you have to deal with it. And this is a crucial point of the event reasoning I mentioned previously. So if you want to reason about something, the events need to be in order. So what can you do about it? So you can build windows, and you need to apply at first a watermark strategy. A watermark is the endurance that anything what happens, a watermark determines a point of time. There's nothing behind this watermark is actually considered within the stream. So this is a small example. You can see here numbers, and then the watermarks that get emitted. So at first, it sees a maximum of 15, and what you apply in an out of orderness, you need to measure that. You subtract that from the original timestamp that comes in, and then you create some sort of buffering, because you always subtract a value, and you actually delay time in that matter. So, but time moves only as fast as events are coming in. It's not what Florian explained as processing in event time, and we are using event time because we want to have this replayable stream. So that means whatever we do, if we go to the beginning of the stream and we replay the whole thing, we want the same results as before. If you do it with a wall clock, in terms of processing time, that would not be the case, because it relies on CPU and all kinds of stuff. So it's not deterministic in that case, and we need to have it deterministic. So to verify that, so imagine you're in a bus and people are getting in, and there's always the person that gets late, but the bus needs to leave. But people are angry. But anyway, the bus needs to be at some other point in a certain moment of time, and that's what stream processing is all about. You want to be on top of the stream and not process historic data. So that means people who are actually late won't get on the bus, and hence also won't get processed in the stream processing. So that's why this is called late arrivals. It happens sometime, but you might ask, so well, how can I, let's say, mitigate the problem? So the only thing you can actually do is you have to analyze your data. So you need to understand what values are coming in, what timestamps do they carry, and if you see, you start with some, let's say, out of orderness of an arbitrary number where you think, well, that might be some good fit, and then you create metrics out of it. You need to measure it. You need to have data on it to prove your point, and then say, well, the average is delayed by, let's say, 15 seconds, and then you can set an out of orderness of that, and so you more or less try to ensure that all your data gets processed right away. So, but that's not, for us, that worked out a decent amount of time, but we soon discovered, well, distributed systems not always behave as we want to have them. And imagine some of the devices run out of time sync. So that means it doesn't have the proper time, so it sends, in the worst case, timestamps from the future. So imagine, again, going back to this bus example, the first person steps into the bus and says to the driver, well, it's not 12, it's 12:05, we have to leave, and he leaves, and actually all the others are looking and say, well, it's 12, what's happening? So what actually happens is one of the participants advances the event time really fast, and this is a major drawback for all the other participants in that system, because they are all considered as late. And as bigger this gap gets, as more the problematic is. And you need to somehow get this configured and somehow need to manage it. Because going back to our original use case, we have a production line and we need to detect states, and we can't just, let's say, lose some data. Some of the data is crucial for the processing, and we need to somehow collect it with let's say, negotiating a decent amount of latency. So what have we done? So I'm going to step deeper, because it created a lot of headache in our development phase. So what did we do? So we collected from all the senders timestamps individually, and then we built up a global minimum. Imagine every chain let's say in a team, or if it's a good team, so well, is as fast as the slowest participant. And so we said, well, this might be something for us as well, so we need to find a global watermark over all the senders, and then we build up a global minimum, and that we use as watermark. Well, it compromises some sort of latency, it introduces further latency, but it brings us to a point where we can say, okay, we are able now to collect more of the data. So further, you have a use case, well, again, some of the senders loses network connection. It stops sending data, that's pretty bad. And so the watermark, if you build a minimum, we're not advanced. So that means it stalls forever. And so what we have built is so that the processing of a watermark is quite similar to a process function. So you can process every individual element and extract the data out of it, what you need for the proper watermark generation. And what we then do is, as you have seen previously, we build a hash map, we collect all the data, and then we, let's say, store it. And usually, Flink works that way that not every watermark gets emitted right away. So not every item you see is emitted let's say, straight away, because it requires some further downstream computation in the cluster and synchronization about watermarks. So you should not create on every event a new watermark. And so there's a concept of periodic emits. So that means this watermark generator is periodically queried by Flink, and thus makes it possible to send then a watermark, computed all of the last seen watermarks out of it, build a minimum, and then send it straight away. So that's what it's basically doing. And that helps us a lot to more or less find proper values for the watermarking strategy. And further, what you need then to do is, if you have let's say, stalling sources, you want to still be able to create a watermark, so you need to get rid of them. So you see, well, there's some of them in idle, so you get just throw them away, and they're not considered in the computation. You can see that, and so bring everything together. There's this emit function, and then you actually do this computation, and then you apply your out of orderness, what I have explained previously, and then this works out the way better than before, because not individual participants of the streaming can advance the watermark significantly, so that others, let's say, suffer from that. So the stream gets way more deterministic. So that was a major, let's say, bummer for us, and so we had to learn on that. So that was basically it. So basically, that's problems you can handle with your source code. But there's also, let's say, you have a distributed system with Flink itself, so things can happen there. And Florian, you might tell us a little bit something about failovers in Flink and what Flink offers for us.
Yeah, sure. So as our Amazon CTO always says, everything is failing all the time. And this is also true for Apache Flink. So if you run on Kubernetes, for example, virtual machines usually try to treat it as disposable hardware. So if something fails, you don't want to stop your whole application and shutting everything down, but you want to resume your application, restart it, spin up new infrastructure, or do something similar. And for this, Flink offers checkpoints and also save points. Those sound very similar and are very similar, but they try to achieve two very different things. So we discussed previously on fault tolerance, exactly once processing guarantees, at least once. So this basically defines how our checkpointing is behaving. So let's say we have an incoming stream, one of our worker dies, so this means something is not getting processed. So how do we restart our application that everything is getting processed? This would mean that we need to have certain checkpoints. So a checkpoint is basically a record that is running through our stream, and then at a certain point it gets checkpointed. This means the state is stored in a durable data store. Usually this is outside of the Flink cluster. You can also define it that it's on the job manager, but in a production environment, you would have this on a durable storage, such as Amazon S3 or any other object storage. So we define a checkpoint strategy, let's say every 30 seconds. So this would mean that every 30 seconds, the state is stored into an external data store. So what happens now if it fails? So this would mean that we restart the application and we restore from the latest checkpoint. Of course, this would mean that we can process some record twice. Because maybe we did our checkpoint, 20 seconds pass, and then our application dies. We restart, so we reprocess 20 seconds of data. So how can we eliminate that? Because that's not exactly once processing semantics, right? So we would define exactly once checkpoint. So this would mean that we checkpoint the data, and if it's restored, we start from our checkpoint, but only we process the data if it has not been processed already. So what is a save point, basically? A save point is when you update your application, you want to have a save point. This is to have a maximum compatibility. If you, for example, do version upgrades from Flink 1.17 to 1.18, you want to create a save point. And it's a manual work, so you don't have save points automatically by Apache Flink. You need to trigger a save point. You can do this via the REST API. You can trigger a new deployment, like a new application version. This also creates a save point of your application. If you're using something like Argo CD in your CI/CD pipeline, you can just increase the save point counter, and it will create a save point for your application. So if you want to update an application, create a save point. If you want to recover your application, use the checkpoint. And this is done by Flink itself. So you don't need to actually handle that. And all the connectors that come with Flink for Kafka, Kinesis, certain databases, they already implement this checkpointing behavior. So they buffer something, or any operators are buffering records. So all this state is checkpointed and stored in this durable data store. So now we heard a lot of concepts. We heard event time, processing time. We learned about state. We also learned about checkpoints and save points. So those are the fundamentals of Apache Flink. Of course, there are some more that you can dive deep for a lot of weeks or even months. You can read books about it, like I did. But we now want to understand on how Krones is using it, actually, and what their application is looking like. So, Emil, please show us what your application is doing.
Yeah, sure. So basically, a Flink job is what I meant is a graph where you, let's say, process step by step the event stream. And at first, we decided to go with Kinesis because it's a decent choice for us, because it's also in AWS, it's a managed service as well, and it works pretty well for our use cases. Then what usually makes sense is when data is coming in, not all the data is like you would expect it to be, and so you have to normalize it in some way. So you parse it, you check whether there's something in it, especially in event-driven systems, there might be versioning, and you don't want to process all the versions, so you want to get rid of some of the data, so you do that in this particular step. Also, we use it to calculate some metrics in terms of what data from which senders are coming in and how many of them are coming in. And also we create some metrics about how is the overall latency within the job, that we can always measure our success in terms of metrics, so we can see, well, after one release something is working better or it decreases and there might be some potential problems, and we can dig deeper into it. So that makes it pretty strong. And the next step is then obviously, well, by the semantics of Flink, some of the sources, like the Kafka source, that brings watermarks with it, but some of them do not. And if you see, well, you have a first step to normalize the data, you actually don't want to create watermarks or, let's say, consider events that get filtered out into the watermark computation. So that's why you do that usually afterwards. And I mentioned it all. So what I previously also mentioned is the ordering of the data. And at some point, if data comes unordered, that means scattered around shards, you somehow need to bring them together. And so you need to sort them, because you want to reason about something hasn't changed for 10 minutes, or some event happens after another one, or you want to compare two events. Let's say you want to compare a temperature against a benchmark value, which also comes from the machine. So you need to be able to process that in order. So if the order is not persisted, you have, let's say, a huge problem in your event reasoning system, because you can't reason anything. So that's why we need to sort data. Sort data is not perfect, because it's more or less a workaround and a compromise about the sender from the machine. Because I mentioned the stream manager, because it offers a lot of other opportunities for us in terms of failover. So we decided, well, we need to sort the data afterwards. We could easily write a different sender, but then we needed to write a lot of code, and so we decided not to do it. And so the next step is what we have also seen is calculate the metrics. So we want to have some averages, statistical values, calculate over temperatures that are coming from the machine. And also we want to present it to a user. So we sync that out. So in Flink, you call it sync. So you can actually plug it to any operator you want. And you say, well, this data we want to send to a third-party system like a database or something like that. So you collect it. And then you can visualize the data there. And the next step is coming back to the rule reasoning. So we have this, each of them, let's say, temperature above threshold for 5 minutes or something. So that's evaluated here. And then we saw where there's a stream of states now coming out of that reasoning. And so we bind that all together and build up a final result. And this result then also gets through a sync. So we sync that again to Kinesis because we want to build up also downstream systems to be able to replay the result stream in terms of they need to be idempotent in an event-driven system. That makes a lot of sense. So you don't process all the events, so you can detect, well, this is the same event what I have seen before, so you don't trigger further downstream computations. So that makes a lot of sense for us, and so we sent them down into Kinesis and downstream system. There's actually one consumer that is consuming all the results out of it. And so that turns out pretty well over time, and with more and more, let's say, customers onboarding, it gets more challenging to create watermarks and everything. You see, if you look at the typical SaaS deployment, you can go for a proper isolation in terms of a full siloed application, and you can go for a shared pool resource, so everything in one. So we started with the shared pool resources because it gave us a lot of opportunity to get started fast, but it turned out a lot of senders behave differently. And so what we invented was, what means invented, but we actually took the chance to isolate some of those senders into what we call buckets within the same job. So we cloned the whole job graph, but we filtered the values out for the individual senders, and then we sent it to the individual job graphs within the same job. That further gave us the opportunity to isolate some of them and to mitigate risk of complete failures. Hence, still, everything is running on the same job. That brings different challenges with it, but it solved a lot of problems for us, and it made it more so we were able to monitor it very, very granular on a level of dedicated senders in terms of customers. And so coming all of that is like going with Flink is a real journey, I have to say. So it was from the beginning, you read through the pages and you see, well, there's event processing, and you get started first because you think, well, it's pretty much easy. And we wanted to do it, so give you an overview of what we are going to do in the future and what we have learned. So some of them in the hard way, in production failures, some of them before they occurred, but it is a complex framework, and it has a steep learning curve at the beginning, but it offers so much for let's say for our use cases that we spend a lot of time learning it. So, and what we can see is there is a break-even point at some moment where you have so many customers that it makes sense to run them completely isolated in an isolated environment. So that you eliminate the completely noisy neighbors. And so for real critical application, that makes a lot of sense. And so that can be achieved by managed Flink, but you can also go for Kubernetes deployments. You can actually decide whether based on your use case and the requirements and also the technical knowledge of the team, which is pretty crucial if you go, let's say, on a Kubernetes journey and you haven't any experience in the team, so it makes it quite challenging. But it also decreases the complexity of a job. So the watermark generation is pretty easy because one sender usually can't disturb another sender. So you eliminate completely the noisy neighbor stuff. And also failures of an application don't hit all of the customers. Only single customers are like in the blast radius of such an occurrence. And also imagine if you want to replay the whole stream for a bunch of customers, so that's way more data than an isolated customer, so the whole replaying process is way fast. And you might ask, why do we need to replay stuff? So at some moment of time, your state, when you deploy new versions, you need to rebuild the state for whatever reason. And then a streaming technology like Kinesis or Kafka comes into play, and you can say, well, I want to replay the whole stream from the beginning, and then you can replay the whole thing. And you, as we implemented event time correctly, our stream is deterministic and yields the same results. But this is significantly faster if you do it for one customer compared to if you do it for a bunch of customers. So to combine all that, so lessons learned. So it's kind of funny to say, because you have a Flink documentation. It's quite, let's say, decent, but every word in that counts in some way. You always run into some problems, and then you reread the documentation and say, well, what they're saying that in this particular 2 words, it makes a lot of sense, but you're searching for that a few days, and then you come up and find a solution in the documentation. Well, you can also go for Stack Overflow, but mostly people are then citing the documentation and say, well, there it is. So there was some learning, so you have to be careful while reading and applying all the concepts to your system. And that makes it pretty challenging. Flink offers everything in terms of technology, but as a company working with data, you actually need to understand it, and it's something what often gets overseen. So you need to work with your data, and you need to understand all the semantics of your data that your machines are producing in order to apply really stream processing. That if you, let's say, anticipate some of the stuff, so it won't come as you anticipated, because it always like, yeah, as Florian said, it fails eventually. And further, that what I explained with the stream management and the edge devices sending data, you need to get your sources right to send the data, let's say, as a good fit for stream processing. Like, where we can sort the data, but you could argue, well, it makes a lot of more sense to do that. You actually choose better sharding keys to send that into Kinesis, and the data arrives sorted before actually reaching the Flink job. And so you have to also deal with a little bit of out of orderness, but not with this kind of range that introduces a lot of latency. So, and I explained it here, metrics. So you need metrics. So the thing is, if you don't see what your system is doing, you're literally blind, and that's really complicated if you want to debug problems. You can write, so Flink has a real good use case framework, but also you all know that writing unit tests, and you actually do something where you think, well, this is how it's being used. But data behaves then differently, and then you see, well, it doesn't work out the way I wanted to have that, and therefore you need metrics to see that. After release, you need to monitor all your data and derive the right actions out of it to be successful in your streaming journey. And to sum that up, so for us, the Amazon Managed Flink service is a kind of a real good fit for all the use cases we had, and we were, let's say, if we haven't done if that would not be available for us, we probably would not have been gone on this journey, and we would not be able to implement our use cases. So that was pretty much a real valuable input for our, let's say, streaming journey. Perfect. So yeah, so thanks to you all for attending. So that's basically it from our tech talk from today. And after that, we do a Q&A session. Maybe you have some questions for us. We do that only offline, so all the online participants are next time invited to join us here or in a different location in person. And we are happy to answer your questions right away. And also, Florian, thanks for being here as a guest. So that was really awesome.
Yeah, thank you, Emil, and also thank you to the Krones team for hosting me here. And I'm looking forward to the next Tech Talk.
Yeah, thanks for that. And have a nice evening and stay tuned.